good to be back with you. Today I'd like to talk about circular orbits. We're very fortunate to live in a time when getting to orbit is getting easier. Companies like SpaceX and Blue Horizons are putting up experimental rockets right now. As I'm doing this, they're beginning to be successful. We think they might become successful in the long run. Lots of countries are launching payloads for the first time. It's getting easier to get to low Earth orbit. Wouldn't it be good if we knew a little bit about the physics of what has to happen in order to get there? So what I want to do is talk about the simplest orbit. It's a circular orbit, and explain what it takes to get there. All right. So here I don't have an entire planet in my little office, but I have Earth. Okay, I got to see it's labeled. It says Earth. Well, or electron, I guess, depending on what you want. But this will be Earth, and I need a rocket. I need a smaller one than I tried last time. This is a socket. So this is a socket rocket. That's a dad joke right there. Anyway, so this is this is going to go around the Earth. All right. As it does this, what's going on is that the Earth is a massive body. It has a force moving towards the center of the Earth. Anything near it is going to be drawn towards the center of the Earth. This rocket that's going around the Earth, all right, is essentially falling towards the Earth. All right, it's in a circular orbit, so it's accelerating towards the center of the Earth, and whatever the local acceleration is. When the acceleration of the rocket is equal to the acceleration that would be caused by the force of gravity, you've got a circular orbit. All right, and the simplest way to do this, or to explain this that I can think of, is let's just start with Newton's law. Okay, that's about as simple as a law gets. All right, and let's just write this out in a little more detail. Well, ma, that's mass of the rocket, okay, times v squared over r. Okay, where that's the velocity in your orbit, tangential velocity. There is no radial velocity since you're in a circular orbit. And there's the radius from the center of the Earth. Okay, so what's going on here is if that's the Earth, and if you're looking at this from the North Pole, you'll actually be orbiting that way. All right, that's the satellite. Satellite, there we go. All righty, and so your orbit, let's see, your height, or your radius, I should say, is that. RO, radius of your orbit. So it's the radius of the Earth. Let me get out of your way here. It's the radius of the Earth plus the height of the orbit above the surface of the Earth. Okay, so that's what that R is right there. I want to call that RO. And this is the universal, or the Newton's law of gravitation. Right. Well, that's G, M, and I'll call that the M of the rocket times mass of the Earth, or r squared. That's Newton's law of gravitation. All right. Now, that g right there is not the acceleration of gravity. That's little g. Big G is the universal gravitational constant. All right. It's a very, very different number. It's sometimes 10 to the minus 11th. I'll show you here in a second. But the big idea here is that number right there is a universal constant in nature. It's like the speed of light. It's the same everywhere. It doesn't change. It's not an acceleration, and it doesn't depend on where you are. As I'm making this, at least as far as we know, this is constant everywhere. It's the same on Alpha Centauri as it is here. All right? So let's take these two pieces and set them equal to each other. If there's all these equal signs in the middle, I can get rid of this stuff in the middle and do this. Should have a 0, I suppose. Okay, well, a little nasty, but a lot of stuff's going to cancel out. Does it make sense that the mass of the rocket cancels out? I mean, does it make physical sense? Well, yeah, it does. If it didn't, it would mean a little rocket would orbit at a different speed than a big rocket. Okay, Sputnik wasn't much bigger than this. All right, a little bigger, about the size of, I don't know, basketball, bigger than a basketball. But if I could lift the weight, I could hold Sputnik. All right, the International Space Station is, I want to say at least 100 meters big, really big. All right, the Hubble Space Telescope is the size of a delivery truck. All right, if that didn't cancel out, all those three bodies would orbit at different speeds even at the same height. Well, that's nuts. That can't be. And that's great. So this cancels out. That's good to know. All right, this and that cancel out. So what I'm going to get, once you do the push a few symbols around, is this. Okay? That's the velocity to be in a circular orbit, not an elliptical orbit. That's a little more complicated. But for a circular orbit, that's what you get. All right? And it turns out to be also, that's half the escape velocity, just in case you're wondering. Okay, so let's maybe put this over here and crunch a few numbers. Okay, it'd be really good if I could just sort of click and drag, wouldn't it? But this is a state school. I don't have a board like that. Alrighty, so there, you got it here. Let's put some numbers down. Now these numbers are going to be really weird. Some of them are going to be very, very small, and some of them are going to be very, very large. We're eventually going to wind up with an answer that's of the magnitude about 10 to the third. So it's something not too crazy. Okay, G as far as we've been able to measure. Okay. Okay. Now the units I always have to check. Meters cubed over kilograms seconds squared. That seems like kind of a crazy unit. You're never going to look at that and go, oh, well, it's obviously that's what it should be. Now, this is just the units that are required to make Newton's law of gravitation work out. So the next one we need to know is the mass of the Earth, which we really do know. Really smart people have figured this out. And this one is a really big number, but at least the units make sense. It's just kilograms. Okay. That right? 9722. Okay, that's correct. And we don't generally need those two numbers by themselves. We almost always need the product of the two of those. And you can look at this, multiply these two, and look at the magnitudes there. It's going to be something around 10 to the 14th or so. So and it is. So if you look, check this out. Just give me a second here. 10 to the 14th cubed. Oh, sorry, meters cubed seconds squared. Okay, and again, funny units. Meters cubed seconds squared. Well, that's just how it is. So all we have to do now is multiply, take that and divide it by the radius of the Earth. The radius of the Earth we also know. It's 6,378 kilometers, but we need it in meters. There it is. By the way, Eratosthenes, an ancient Greek, knew that number to within, a few percent. Okay? So we've known this for quite some time. And I want H to be 400 meters. That's about low Earth orbit. Okay? 400 kilometers, it's about 400,000 meters. Low Earth orbit's out also about 250 miles. So when the shuttle goes in, well, it used to go into orbit, and the space station is in orbit, and all these other things are in what they call low Earth orbit, or sometimes they just abbreviate it as LEO. That's pretty much low Earth orbit. There's no one number, but that's pretty close. So let's just do this. 3.985. Always, always, always check your units. Keep your units. If the units are right, the numbers will pretty much come along for the ride. If your units are not right, your numbers are very unlikely to be correct. So if you throw units away, you've given up a very powerful tool for checking your answer. So hang on to them. So I need this to be 6378 plus 400. And if you do that, we'll get out of your way here so you can see this. 7669. 7669 meters per second. Okay? So is that fast or slow? That's crazy fast. All right? This is the speed of sound in meters per second is like 343 meters a second, I think. So this is on the order of Mach 20 at sea level. And I'll have to check. If you want it in old-fashioned sort of caveman units, it's 4.7, what is it, 765 6.5, that's in miles per second, okay? Again, crazy fast. So when somebody says, well, can't we just take a giant gun and could we just shoot something into orbit? No, you can't, and this is why. These numbers are so high. If you tried to get any kind of projectile going through air that fast, it would very, very briefly turn into a plasma, and that'd be about it, okay? And remember, this is just the velocity once you get there. This represents kinetic energy. There's also enough potential energy to get you, or your payload I should say, 400 kilometers off the surface of the Earth. So if you want to get into orbit, you have to have kinetic energy compatible with that, plus 400 kilometers worth of potential energy. That's a lot. That's why rockets are so big. All right? So anyway, let me get out of your way one more time here so you can see the calculations we did. I hope this helps, and I'll see you next time.